Let's embark on a captivating journey into the realm of statistics, where we'll unravel the mystery of variance, making it an exhilarating adventure rather than a mundane mathematical concept. Variance, in its essence, is the storyteller of how scattered or tightly clustered a set of data points is. Imagine it as the measure of unpredictability or the diversity of outcomes in a game of chance, painting a picture of how much individual results can deviate from what we typically expect and from one another. A variance of zero is like a serene pond, where every data point is a leaf resting calmly at the same spot. No surprises, no deviations.
To breathe life into this concept, let's play a game with a six-sided die, a simple cube that holds the fate of numbers 1 through 6. The magic number here is 3.5, the average roll you'd anticipate over many throws, not found on any face of the die but existing as an expected average. Delving into the enigmatic average of 3.5 for a roll of a six-sided die demands a brief detour into the realm of expected values. This magic number doesn't appear out of thin air but is the result of a straightforward calculation that averages all possible outcomes. Given a fair six-sided die, each face, bearing numbers 1 through 6, has an equal chance of facing the sky when the die settles. To find our expected average, we simply add these numbers together, 1 plus 2 plus 3 plus 4 plus 5 plus 6, and divide by the number of sides, which is 6. This calculation, 21 divided by 6, unfurls the average roll as 3.5. Though you won't see a 3.5 on any die, this figure represents the mathematical heart of probability. It serves as a beacon that guides us toward understanding the expected outcome over a vast number of rolls, revealing the balanced midpoint in a sea of chance. Now, let's dissect the variance for this game. We'll take each possible outcome, the numbers 1 through 6, and calculate how far each deviates from our magical average, squaring these distances to ensure we're only dealing with positive values, as distances are not concerned with direction. Here's where our calculation becomes a blend of prediction and reality. Each squared difference is weighted by the likelihood of its corresponding roll, which, in the realm of a fair six-sided die, is a 1 in 6 chance for each number. Determining the probability of each outcome isn't just another arithmetic process, it's the essence of expectation, where we balance what could happen against the backdrop of what's likely to happen. Before we leap into the world of variance calculation though, it's pivotal to understand the deeper reason behind squaring the deviations from the mean, beyond just ensuring positivity. When we square these differences, we're not merely avoiding negative numbers, we're embarking on a quest to emphasize and penalize larger deviations more severely than smaller ones. This mathematical maneuver elevates the impact of outliers, those rogue data points that stray far from the crowd. By squaring the distances, variance becomes a more sensitive and nuanced measure of dispersion, adept at capturing the full spectrum of variability within the data. This approach ensures that the variance tells a comprehensive story of how data points spread out, highlighting not just the average distance from the mean but the intensity of their divergence. After performing the statistical ballet known as calculating variance, we arrive at a variance of 2.917. This number may seem abstract, but in the context of a six-sided die, it tells a tale of considerable spread. It indicates that the outcomes of our rolls are not whispering closely around the mean but are instead engaging in a lively dance, spaced comfortably apart. Reflecting on this dance, we notice it follows the rhythm of a uniform discrete distribution. This fancy term simply means that each roll of the die, each leap in the dance, has an equal chance to land on any number from 1 to 6, showcasing a perfectly balanced array of outcomes. Understanding variance in this light, as a 2.917 in our die game, illuminates the nature of our data. A high variance signifies a grand ballroom, where each data point dances far from the mean and from each other, reveling in the space to express its uniqueness. Conversely, a low variance is a cozy gathering, where outcomes huddle close to the mean, sharing much in common.